Oh no, a graph. It's okay. So all we're going to do is we're going to take that brick and noodle activity and the match activity and we're going to plot it. So we're going to pretend that we're able to capture the energy and we're going to plot it. So I'm going to abbreviate potential energy for PE. So these are called potential energy diagrams. Okay, the first one I'm going to show you is for an exothermic reaction. So the match and the brick and noodles were both exothermic, meaning they release heat, as in exiting heat. So I'm just going to draw a y-axis and an x-axis. So just like your textbook, the y-axis is going to be potential energy, usually in kilojoules. So that's just energy. And the x-axis has a fancy name in your review book called reaction coordinate, but it's essentially time. So what happens over time? You know, in chemistry, we like to use fancy words. Okay, so my brick and my noodles started at a certain potential energy, right, and the match. So where I started, right, is, let's say, 50 kilojoules, and here's 0. So if I have my brick and noodles, those were my reactants, right, that's what I started with. They have a certain amount of potential energy. And these are called, right, the reactants, what you start with. So the way they like to draw this is they like to say from the 0 all the way to the top, that is considered the potential energy of the reactants. So whatever you're starting with, match, you know, wood fire, whatever. Okay, in order for the reaction to happen, I had to push the brick a little, right? Or I had to strike the match. So I had to put energy into that. So the energy I had to put into that, I'm just going to put it there, raise the potential energy, right? So the brick standing upright versus tilting. Tilting had more potential energy, more potential to do damage. So what I'm going to do is I'm going to label that with a different color here. So what we call is the difference between the peak, I'm just going to say that ended up there, and what I started with. So striking the match or pushing the brick is called the activation energy. So this is called, and I'm just going to abbreviate, everything's in the review book, activation energy. So the energy to activate it. So if I say that that's now 60, 70, 80 kilojoules, can you figure out what my activation energy would be in terms of joules? So see if you can figure out how much energy is the activation energy. So it's 80 minus 50, so that would be 30 kilojoules. Okay, so now another thing we need to label is the top of the peak. So the top of the peak has another name. The top of the peak is very similar to the activation energy, only it's called the activated complex. So close, these words, so easy to confuse. So the activated complex, the potential energy of the brick right before it fell, or the match right before it caught fire, is the amount of energy from the 0 all the way to the top. So this is the activated complex. So the potential energy of the activated complex, there we go, was 80. And let's just go back. So the potential energy of the reactants is 50. Our activation energy is 30. Our activated complex is 80. Okay, so as the reaction progressed, right, especially you could see it with the match, it's burning, 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 releasing heat, and then it is a crispy piece of wood. And that is where I ended, right? So wherever I end, let's see, green I haven't used, is going to be the potential energy of the products. So here I have a brick noodle mix, right? Brick nude. So these are my products, which are a lower potential energy. And let's say this is, 20, right? So this would be 20 kilojoules. Okay, now I went from 50 to 20, right? So I started at 50, and I ended up with 20. Well, there's this idea called the conservation of energy, right? So I can't just, energy doesn't disappear, right? The energy of the match went into the air, right? Heat, light. So we have to be able to label that as well. So the difference between the potential energy of the products, and you're going to see it like little lines like this. So they're just going to put a line here. That's 20 where I am at the products. And then my reactant started at 50, right? So the difference between those two is called the heat of reaction. So how much heat was lost when the brick slammed down, right? Sound energy. How much heat was released when the match was burning? That's delta H. So when it is an exothermic reaction, remember delta H is always written as a product, exothermic. So the equation for the heat of reaction, again, delta H is called the heat of reaction. It's not the first time you've seen this, but we really went very fast when I introduced it to you. I told you we would be coming back to it. Is defined specifically as the potential energy of the products minus the potential energy of the reactants, not the other way around. So if I was going to plug that in to the heat of reaction, the potential energy of the products is 20, running out of room here, so I'm just going to put it here, minus the potential energy of the reactants, which is 50. So in this case, my heat of reaction is negative 30 kilojoules. Remember, exothermic is negative. Okay, I'm going to stop here and do another screencast on an endothermic potential energy diagram.